with it. Okay, it says diamonds are a naturally occurring form of elemental carbon. Two stable isotopes of carbon are carbon-12 and carbon-13. Write the symbol for each isotope using subscripts. And so you can see that the first one is 12 over 6 C, that's carbon-12, and for carbon-13 it's going to be 13 over 6 C. Okay, so do problems 19 and 20, please. Okay, so for number 19, first one, you'd say 16 over 8 O, then it'd be 17 over 8 O, and then 18 over 8 O. Okay, so in number 20, what they want to know is how many neutrons are in each one. And so the first one, you would take 50 minus 24, you'd get 26. 52 minus 24 would give you 28, and 53 minus 24 would give you 29. Alright, now we're going to get into something a little bit more difficult, talking about the atomic mass. And, you know, if we wanted to talk about the mass of an atom, they're so small, it just doesn't make any sense. They're just so incredibly small. So instead, what we do is we use the mass of the atom compared to the mass of a carbon-12 atom. And so we actually make up a unit called the atomic mass unit, or AMUs. And what we say is that if we have an isotope of carbon-12, so in other words 6 carbon atoms, 6 protons rather, and 6 neutrons, it has exactly the mass of 12. Therefore, each proton and each neutron has a mass of 1, or the atomic mass unit would simply be 1/12 of carbon-12. But it is easier to think about the fact that an atomic mass unit is the mass of 1 proton or 1 neutron. So once you know how many protons or neutrons are in there, you would know how many AMUs that they would have. So mass of a single proton or neutron, 1 AMU. And what happens in nature is there is almost always a multiple amount of isotopes. You know, 2, 3, 10. I mean, there can be a lot of different isotopes depending on the element. And so there's a mixture in there. And if we want to find the atomic mass of an element, what we do is we create a weighted average of all of those atoms. In other words, you know, it doesn't make sense if, let's say we're talking about carbon. Carbon-12 is by far the most common element that you can find. Probably 99% of what you find for carbon is carbon-12. And then, you know, a very small fraction of a percent is going to be maybe carbon-13 or carbon-14. So we do a weighted average, and we take the percentages that exist times its mass, and then we add those together. So take a look at this chart here, and you see that hydrogen 1 is the most common. 99.985% of all the hydrogen you find in the world or in the universe is carbon 1. And it has an atomic mass of 1.0078, and that, yeah, well, just don't worry about it. Well, normally we would say it's 1. I mean, it's close enough, we'd say it's 1. Carbon 2 does exist, but only about 15, 15/100ths of a percent. But it has an atomic mass of 2. And then hydrogen, that'd be hydrogen, by the way. Hydrogen 3, doesn't exist very much. In fact, it's mostly man-made when we use it. But you can see that the average is going to be 1.0079. So a little bit of the hydrogen 2 in there to factor up, and so on. Probably, let's see, a little bit better one. Let's take a look at chlorine down at the bottom. It's probably a little easier to see the difference here. Notice that there are 2 isotopes, chlorine-35 and chlorine-37. 75% of chlorine exists as chlorine-35, so that's going to have a really close to atomic mass being 35, so 34.969, and then 24% is carbon-37, so there's 36.96. Now you don't just average those together, because if you did, you'd get 35.9 something. But what we do is we take a weighted average. We take 75% of the 34.969 and 24% of the 36.966 and add those together. And that gives us our weighted average between those two. Alright, so take a look at this. It says the atomic mass of copper is 63.546 AMUs. Which of copper's two isotopes is more abundant? So is it closer to 63 or 65? Well, that's pretty obvious. It's closer to 63. So the isotope of copper 63 is the more abundant one. Take a look at the questions down below. Stop the video and come back when you're done. Alright, so if we look at the first one, there must be more boron 11 than boron 10, because 10.8 is closer to 11 than it is to 10. And if we look at the second one, where the atomic mass of silicon is 28.086, you must assume that the majority of the isotope is isotope 28, and the other ones are probably just very small fractional percents. Alright, to calculate the atomic mass of an element, here's what we're going to do. You're going to multiply the mass of each isotope by its natural abundance. So take your isotope, figure out the percent, change that percent to a decimal, and then multiply. And then what you do is add up the products. So if we're talking about carbon, carbon 12 existed as 98.89% carbon 12. So you would take that as a decimal, 0.9889, and then you take carbon 13, 13.003, times its percent as a decimal, very small percent now, so 0.0111, and then add those two together, and that would give you the average atomic mass. Alright, so take a look at these problems. Notice that for the element X, whatever we're talking about here, the isotope has a mass of 10.012 and a relative abundance of 19.91, and the mass 11.009 and relative abundance of 80. So if you go down to where they go to calculate, you can see they're taking the 10 times the 19% as a decimal, so 0.1991. That multiplies out, gives you 1.993. Second one, they're taking 11.009 times 0.8009, and that equals 8.817. Together, you add them up, you get 10.81. And that should make sense that it's closer to 11 than it is to 10. Okay, I want you to do questions 23 and 24, and we will talk about those in class. So I want you to have those done for class time tomorrow, or yeah, whenever.